welcome to this course on compiler design. So, in this course, we will try to see like the different phases in the design of a compiler. But to start with, it apparently seems very much difficult that given a language, how do we translate it into another language. But at the end of the course, we will see that certain parts of it can be automated and certain parts of it depends on the experience and the expertise of the programmer to develop the corresponding portions of the tools. So, there are different parts of this course, while some parts of it have got formal background on automata theory. Other parts, so they are guided by a few rules. For some of the programming language constructs, the rules are well defined. Now, if we come across a new programming language, then we need to redesign those rules. Okay. So, in this course, so we will try to have an overview of this entire process. So, to start with, in this introductory lecture, so we will try to see like what do we mean by a compiler, then compiler applications, the phases of a compiler, then challenges that we have in compiler design, then compilation process. So, we will see an example by which we will try to illustrate like what are the different phases of a compiler, and we conclude the lecture by summarizing what we have in the introductory part. So, to start with, compilers have become part and parcel of today's computer systems. Now, if you look back the early computer systems that were developed, so they are huge computers in terms of the hardware, and it required a good amount of space to house that particular computer. Apart from that, so apart from this electrical and electronic challenges, the other part of it was to make it work. Make it work means to make it do some useful computations. So, for that purpose we needed to write a few programs, and those programs are to be entered in some machine level language. So, as we know that computers ultimately they understand binary zeros and ones. So, we need to write the program which is meaningful to the computer in terms of zeros and ones. So, you can imagine like the amount of difficulty that you will have. So, if you have to write even a 10 line program into binary, convert it into binary zeros and ones which are meaningful to the computer. So, that so early generation computers, so there this was the main problem, and this translation process from this program, the program that is understandable by human being to a program understandable by the underlying computer was a big challenge, and it was done by means of manual methods by which we know the codes of each and individual instructions, and we do translation by hand. So, that made it very difficult, and slowly the system improved, and today we do not even understand that whatever we are writing and in high level language. So, it is not directly understandable by the computer that is executing it. So, there are a lot of translations that are involved in the process. So, these translations are the essential part that we have in compilers. So, these compilers they make users program computation requirements which is specified by means a piece of program understandable to the underlying machine. So, user writes a program, that program may be syntactically correct, that is grammatically correct as per the language, and the program is hopefully semantically correct, that is the meaning of the program is what the user wants to compute. Okay. For example, if you are trying to write a program which computes a roots of a quadratic equations, then once I write a piece of program in some language, maybe in C or maybe in some Pascal or C++, Java, whatever it is. So, there are two types of mistakes that I could have done. One is I have some grammatical mistake, that is maybe for example, in C language you know that every statement it ends with a semicolon. So, you may miss some semicolon at some place. So, that gives some that is a syntactical error. Maybe I am using a variable which is undefined, which is not defined so far. So, that may also be a that may be also an error, but there is a difference between these two types of errors. In the first type, when I said that I missed a semicolon, so that is a grammatical error, where when I say that I have not declared a variable. So, the machine does not know what to interpret for this particular variable, the type of it, whether it is integer, real, character. So, that is not understandable by the computer. So, the type of operation that we are trying to do on the variable is not well defined. For example, if I am having two integer variable, I can do an addition operation, but if the variables are of type character array, so I cannot do the addition, I can only do string concatenation or say string operations on them. So, there is a basic difference between the two types of errors that we see. One is syntactical error, another when the meaning of the program is not correct. So, that is a semantic error. So, it is the compiler designer's job to catch both of these types of errors, syntactic error and semantic error. So, when the user has specified his requirement, so in the requirement itself we need to analyze whether the requirement has been specified properly syntactically and the meaning of the program is also clear. When everything is all right, then only the compiler will do a translation. So, it will translate the program from the high level language to the machine level language, and that includes complex transformations. So, in this course we will see how those transformations are taking place. So, this transformation will happen accordingly. And with the increase in the complexity of the computer architecture and operating systems, so the challenge that the compiler designers face, so that is also increasing. For example, like say today if you look into any advanced computer architecture system, so it has got many interesting feature. One typical example is the CISC versus RISC architectures. So, CISC architectures we have got instructions which are pretty complex, and the RISC architecture we have got instructions, machine level instructions which are very simple. But the main difference is that in case of RISC, the instructions are of equal size and they take more or less same amount of time for execution, whereas for CISC architecture, so it is the other way. So, it takes the instructions are of variable size and they take different amount of time for their execution. In fact, while you are trying to do some work, so if I give you instructions which are very simple in nature, so you may possibly do that operation in a more compact fashion. Like if I am trying to find the roots of a quadratic equation, okay, then if I have very simple instructions in my hand, I can possibly do that operation without creating much of extra executions. On the other hand, if I am having complex instructions, so some of the instructions may not be very much necessary, some whole part of the instruction may not be completely necessary for some operations, but still I have to take it. So, that way the CISC instructions they are going to be difficult to handle as far as the compiler designers are concerned, and in fact, this movement from CISC to RISC, this happened because of this compiler designers from the compiler designers perspective. So, it was suggested that okay, if I have got simpler machine level instructions, it is easier to generate efficient code. So, with that this is done. So, with the advances in computer architecture, so these challenges that are faced by the compiler designer, so that is going up. So, memory management policies, like today you know that almost all computers operating systems, so they are supporting virtual memory. So, if virtual memory is supported, then so we have to judge like what are the most relevant operations that we are going to do, and possibly we want to keep those relevant portions in some part of memory which is not going to be swapped out to the secondary storage. So, that the operation efficiency is high. So, this way this memory management plays an important role in determining the compiler generated code's performance. On the other hand, the operating systems, the new operating systems are coming. So, they are also having newer features. So, accordingly all the challenges that are faced by the compiler designers, so they are also increasing significantly. So, what is a compiler? So, let us try to understand what is it. So, compiler is a system software that converts source level language program into target language program. So, source language program may be some high level language like say C, C++, Java, Fortran, Pascal. Now, how many different languages have been developed so far, that is innumerable. So, we cannot just go on giving examples, but we can say that okay, so compiler for every language that you design. So, if we want that the corresponding program will be executed by the underlying computer. So, it must be translated into some machine level code, and that has to be done by the compilers. So, compiler is a system software that converts source language program to target language program. So, here the target language means in this particular case we are assuming machine language, but very shortly we will see that it is not necessarily machine level language. So, it may be something else also. Second important thing that the compiler does is that it validates input program to the source language specification. So, source language, any language is specified by means of its grammar. For example, if we look into the English language, so English language has got its own grammar. Okay. So, any English sentence that we write, so you can check whether it is grammatically correct or not by properly analyzing the sentence. So, similarly, when you write a program for some in some language, so we can consult the grammar rules of the language, and accordingly we can say whether the program is grammatically correct or not. So, if the program is not grammatically correct, then the compiler should produce some error messages. So, that is such as, for example, a semicolon is missing, then it can say that okay, one semicolon is missing at this point. Sometimes we also need to produce warnings. So, warnings are like this, that at some places maybe the programmer has not written some specific declaration or specific transformation that is needed, but it may not be an error. So, if the program will execute, but the outcome of the program may be unpredictable. So, we will take a small example, and we will take a small example like, so for example, in C language program, suppose I write say integer x and then x equal to 10.5. So, if we do this, so there is a problem because this 10.5, so this is not an integer number. So, this is a real number and x is an integer as I have defined. So, you see that when the system will try to do this 10.5 assignment to x, so what will happen, it is very much system dependent, because the 10.5 being a real variable, maybe it is given 6 bytes of space or 8 bytes of space, whereas integer x being an integer variable, depending upon the system it may be given 4 to 6 bytes. So, what I essentially mean is that the space allocated to an integer variable and a real variable, so they are not same. So, naturally when you do this type of assignment, the value that will be copied into x is not very clear, it is not very much sure. Okay. So, if you, and it can vary from one computer system to another computer system. So, output produced in one computer may be different from what is produced on the other computer. So, ideally I should write, if I really want that this integer part should be assigned to 10. So, I should write like this, int casting, the type casting has to be done, and then I should write 10.5. So, in this case I am explicit. So, if I write like this, then the compiler knows that okay, what the user wants is the 10.5 value should be taken as an integer value and then assigned to x. So, there are well defined rules by which this transformation will be done. So, it will remove the fractional part and it will take the integer part only and assign it to x. But at this point, what the compiler will do, or what will happen when the program is executed, so it is not sure. So, in this case it will generate an warning. So, this is a warning that there is the incompatible type assignment. So, when you go to the type management or this type checking part of this course, so we will see this thing in more detail. So, what we essentially mean is that it is trying to assign some new value to a variable, and the value may not be compatible. So, that can give some warning. So, there are other types of warnings also that can come. So, many times when you are writing programs and compiling it, so you must have seen many such warnings, and most of the time we say okay, ignore the warnings, but ignore the warnings is not always good, because as I have said that the value assignment may not be predictable. So, as a result your program may not run correctly. So, it is ideally desirable that you remove you take care of the warnings also and take appropriate actions in your program, modify the program in such a fashion that the compiler does not give the warnings also. So, if there are errors in the program, then the compiler does not generate the final target code, it gives the errors and come out, but if there are warnings, the compilers they generate the target code also, but the target generated code may not be very good. So, it may be erroneous. Then primitive systems, as I said, the early computer systems, so they did not have compilers. So, at that time the electronic design itself was so challenging that people did not think about how to about this writing programs in high level language. So, they thought that okay, entering the values through some switches and all, so that should be good enough to judge the underlying hardware, and program written in assembly language and hand coded into machine code. So, after this machine language we have at the next level of programs. So, there was assembly language code, and when we discussed in some courses on microprocessors, you might have seen this assembly language programming. So, the assembly language programs, so they were hand assembled. So, if you look into the processor designer's manual, you will find the corresponding code for each and every instruction, and accordingly every instruction ultimately gives rise to some hexadecimal code, and those hexadecimal code values are entered through manually through the some card reader or some other mechanism. So that the program is entered into the computer system. So, it was very common that okay, so last night you enter your program. So, that you typed, you punched cards a good day, so maybe for 80 line program. So, there are 80 cards. So, 80 cards you punched on a card punching machine, give it to the system, and next day morning you come just to find that at card number 8 there is a syntax error. So, and then again you go back again punch the cards, correct it, and then again give it. So, that was the problem. It was taking huge amount of time. Today we do not even think about that type of situation. So, as soon as we write the program, even a part of it, we give it for compilation and see whether there is any error in that part or not. So, that is the beauty of these compilers. So, that can help us in detecting the bugs much earlier. So, compiler design, it started actually with the language Fortran in 1950s. So, Fortran is the language which is used for which was used for scientific calculations, full form is for formula translation. So, and quite some time, so Fortran existed, and this was so in first compilers, they were designed for Fortran language, and many tools have been developed for compiler design automation. So, as I said that a part of this course, so they have got foundation on automata theory, and accordingly we can come up with some tools, automated tools that can generate the compiler given the grammar of the language. So, it can generate the compiler in the sense that it can do syntactic checks. Okay. So, if there are some grammatical errors in the program, so it can come up with those errors, but it cannot generate code. Okay. So, for code generation part, so we have to rely on some other translation mechanism which are commonly known as syntax directed translation. So, which will be doing this translation part. So, one part of the course is to check whether the program is syntactically correct or not. The second part of the course is to see how we can generate code for the programs which are syntactically correct. So, we will slowly go into these different parts. Next, okay, next we will see. So, pictorially you can think of a compiler like this, it is a box. So, the source program is the input, and this source program is taken as input, and the compiler analyzes this source program, and it generates some error messages. If there is some error in the program, so it can generate some error message. If there are some warnings, so it can generate warnings, and if there are no errors, then it also generates the target program. So, in the maybe in machine code, maybe in some other form, it also generates a target program. Now, at this point of time, so I would like to emphasize that there are another so in general I can say the compilers, they are working as the translators, And these translators, there are two types of translators that you can see in a computer system. Some of them are known as interpreters and others are known as compilers. Okay. The role is more or less same in the sense that both of them translates the source program into machine language program, but interpreter is doing it like this. So, if this is a program, okay, so it has got these program lines in it. So, interpreter will take one line at a time. So, it will take the first line, it will convert it into the machine code and it will execute it. So, if the execution is fine, then depending on the execution, so then it will go to the next statement, it will translate the next statement into machine language and then again it will execute the program. So, it will execute that particular line. So, in case of interpreter, as the name suggests, so it interprets the programming language statements one by the program's statement one by one and executes it. Whereas, for compilers it takes the entire program together, and as this diagram is showing, so it is generating the corresponding target program. So, so given if this is the source language program, so for this it is translated into a machine language program by the compiler, and this entire program can now go into execution. So, it can go into execution and to produce the result, it will produce the result. So, that is the purpose, that is the way this compiler works. So, this entire translation is done in one shot. So, these interpreters, they are good in the sense that when you are designing the program initially, the interpreters may be good because it will go one line by line. So, if there are some error in the program, particularly the logical bugs in the program, then it is easy to catch those logical bugs by means of interpreters. At whatever point there is some problem raised, so we can check the variable values and we can try to see like what has gone wrong. But at the same time, the interpreted execution is also pretty slow, because it is doing one program line at a time. So, it is going to be pretty slow unlike the compiled version. So, it may be advisable that in initial phase of program development we use the interpreters, and at the final phase when the interpreted programs are running correctly, we are happy with its execution. So, we can give the program to a compiler, so that the compiler will generate the target code directly, and this now the target code execution will be much faster compared to the interpretation of the source language program. So, the interpreters, they are working at the source language level, whereas these compilers, they are also working at the source language level, but they are converting the entire program into machine code. So, as far as execution is concerned, it is for the entire piece of code that the execution is being done. So, this translation, so now we will try to emphasize on this line target program. Now, this target program invariably we have assumed so far that this target program is the machine language program, but it need not be so. So, it may be something else also. For example, suppose I have got two pieces of software. So, suppose I have got two pieces of software, software 1 and software 2. So, some input that comes to the software 1. So, this is the input given to software 1, and it is necessary that this input will be should be processed by software 1 and software 2 to produce the final output. So, this software 1 produces some output that goes as input to the software 2, and the software 2 finally produces the output. So, it can so happen like this. Now, if this software 1 and software 2 are coming from two different vendors, so it is very much possible that this format in which this software 1 produces the output is not compatible with the input format of software 2. So, in that case, it is necessary that we put a translator here also, so that this program is this output of software 1 is converted into another output which is compatible to software 2, which is understandable by software 2. So, in this case, this target program that we are talking about is this one, this is the second program that we are this input of software 2. So, here also this compiler that we have, so it is doing a translation, but it is generating target program which is not for machine execution, but for understanding of another piece of software. So, that can happen. So, That is why this target program, when we say, so it need not necessarily be the machine language program, it may be some other format also. So, whenever we need any format conversion type of job, so these compilers, so they can be utilized. So, next we will see so what are the next answer a very simple question, like how many compilers, like if we say that how many compilers have been designed so far, can we enumerate. Okay. And so, this slide is just to make you understand that how difficult may be the job of a compiler design. Okay. So, impossible to quantify number of compilers designed so far. So, so many compilers have been designed. So, nobody can tell like how many compilers have been designed so far. Large number of well known, lesser known and possibly unknown computer languages designed so far. So, after we have gone through this course, so you will understand that designing a new language is not that difficult. So, once you are very clear in your mind that what are the requirements that I need to specify, you will see that designing a new language is not difficult, and whenever you design a language, so you need to have a compiler to translate it into some other form. So, it may be machine code, maybe something else, but we have to do that. So, as a result what has happened is that various people, they have tried to design new languages, and accordingly there are lots of languages that have been designed. So, which are lesser known and possibly unknown computer languages. So, not known at all. And similarly, there are large number of hardware software platforms. Okay, so, hardware software platforms. So, every day some new company, they are coming up with new features, they are adding new features to the operating system. So, if the compiler is trying to exploit those features, then definitely it has to be it is a new compiler, because it is targeting to a new target machine. So, that way this how many compilers, if I want to answer, so it is very difficult to answer in terms of numbers. Okay. Possibly you can say it is infinite. So, efficient compilers are must for survival of programming languages, because if the compilers are not efficient, then nobody will be using that particular programming language. For example, if I design a language say L, and I find that whenever I write a programs in language L, so when it is translated into machine code, the program is much slower than the programs that we have in C language. So, in that case the language L will not survive, people will not use this language L. Okay. So, so that way these efficient compilers are very much necessary for these programming languages to survive. Inefficient translators developed for Lisp made programs run very slowly. So, Lisp is a functional programming language. So, that was designed long back, okay, but it has got very nice features, like programs that you write in Lisp are very much smaller compared to the high level language programs, other high level language programs like C and all. But the problem is the translated version of the program, so they were very slow. So, that the translators designing efficient translator became a problem, was a problem. So, the Lisp programs, they used to run very slowly. So, it was not that much popular. However, with the advancement in memory management policies, particularly garbage collection and all, so it has provided the avenue by which you can have a faster implementation of such translator, and such languages are rejuvenated. So, that way many old languages, they are also coming back, and because of the facility that are provided in the operating system and the underlying hardware, and accordingly the programs they can be generated, the efficient code can be generated for the languages. So, this way answering the question how many compilers have been designed so far is not at all very straightforward, can only say it is not enumerable. Applications of compilers. So, we have got first application is the machine code generation. So, it convert source language program to machine understandable one. So, that is the first, the very first thing, that most compilers, they are designed for this machine code generation. Takes care of semantics of various constructs of the source language. So, this is obviously, so I have to see that the program that is given to given for compilation is syntactically correct. So, that is the syntactic, the semantic constructs and syntactical structures that we have, so that they are satisfied or not. Then limitations and specific features of target machine. So, it has to see like what are the features, like for example, say integers in some machine is allocated say 2 bytes, some machine 4 bytes. In some machine it is a little endian architecture, some machine it is a big endian architecture. So, like that there are different architectural features that we have. So, I have to look into those limitations and features of this target machine to see how the code, the compiler should generate the code. Automata theory that helps in the syntactic checks. So, it can classify the program to be either a valid one or an invalid one, but it does not answer anything beyond that yes and no. But if the answer is no, in that case also the compiler has to give enough indication that what exactly went wrong in the program. Okay. So, so that is the challenge. So, it is not that the compiler designer designs such a compiler such that given a wrong program, it just says that the program is syntactically wrong. Should not be. It should tell, okay, at line number 10 there is this error, at line number 15 there is this error, line number 30 there is this error. So, you see that we get this type of messages. So, how this is actually done, whereas the basic theory of automata, so that will allow us to classify the programs only into two classes, valid program and invalid program. So, it does not give us a hint on where exactly it went wrong. So, it is the compiler designer's responsibility to see that enough information is given back to the programmer to indicate how much where exactly the program went wrong and what should be the action. Compilation also generate code for syntactically correct programs. So, if the program is grammatically correct, then the compiler should generate the code. So, this is the major operations that are done by a compiler in the machine code generation process.